Hi everybody, I'm Pietro Abate. I work at Nomadic Labs. Nomadic Labs is the company that is taking care for the moment of the writing and developing a bit of the Tezos network. We are the people that implement all the OCaml code, they write the notes, I design Mikkelsen, and at the moment, as we speak, there are all the people that also presented the first amendment of the protocol. I was wondering if we can replace the hard fork cafe with the same self-amendable cafe one day. So, today I want to talk to you actually about all the new things that we're doing. Not much of what Tezos is. I hope that you got a fairly good idea of what Tezos is from Matei. I would like to tell you what we are brewing in Nomadic Labs, what are the current state of the network, what are the future perspectives, a bit of the roadmap, and give you a few ideas of what is happening. We are really busy. We have been really busy in the last 2 months because we did the first amendment of the protocol with an on-chain vote. As Matei told you, the particularity of Tezos, we have three particularities. One is that the protocol itself is self-amendable. This can basically allow the community to decide the direction of development of the blockchain. The other big feature of Tezos is the smart contract platform that Mikkelsen is a part of. And to answer the question, what is the difference between Mikkelsen and the Ethereum contract? Ethereum is written in a high-level language like JavaScript, and then it's compiled to the EVM, that it's bytecode. The EVM, I mean, if you're really, really stubborn, you can even read it and understand it. But we are not. I think it's difficult to be confident to understand all the details in the EVM. It's compiled code and it's pretty difficult to read. We wanted to kind of get to a point where the compilation from a high-level language like liquidity that Matei showed you a moment ago was an easy step, and down to a piece of code, Mikkelsen, that it's low level enough, so we choose a stake-based language to be really easy to analyze and to prove formal properties on it. We are, in our company, we're basically all come from universities and research centers, and formal verification, it's one of our strong points. But there is also, Mikkelsen is also high-level primitives, so and primitives to interact on the chain. So we kind of wanted to position ourselves a bit in the middle, to give people the possibility actually to read these smart contracts and to trust the blockchain and to trust the smart contracts that are running on the blockchain. So. Hello. So we have run, I'm not very familiar with Mac. So as I said, we ran our first amendment, our first proposals on the blockchain to allow people to vote in, and we injected 2 hashes of 2 proposals. These hashes are basically the hash of the tarball that contains the ML code that describes the protocol. The protocol itself runs in a sandbox, and the sandbox is safe by the type system and the compiler of OCaml. And in these 2 proposals, with these 2 proposals, we wanted to test to allow the community finally to interact with the blockchain and to maintain these promises, this promise that we put at the beginning many years ago with the white paper that Tezos is self-amendable. We already did, we had the 004 incarnation of the protocol, and the first 3 were kind of they were not really voted on because there were a security update on the initial protocol that we wanted to put in kind of in a hurry. So we kind of forced these upgrades in the protocol. But once the protocol was stable enough, we wanted actually to prove to the community and to ourselves that this is actually possible. So the vote on Tezos works in 4 phases. The first phase is the proposal phase, where people, not only Nomadic, but everybody in these rooms and in the world can propose an amendment to the protocol itself by injecting the hash of the code that implements this amendment. Then there is a second phase that among all the possible proposals in the previous phase, one is chosen. The third phase is a test phase, where this chosen protocol is actually tested live on the chain. This is done to ensure that the protocol doesn't create any major problems. And the fourth phase, it's actually the vote itself. We ask a supermajority of stakeholders to vote for this amendment, and if the vote is successful, then there is an upgrade of the protocol done by the shell. So at the moment, we started this process the 25th of February. We injected the hashes. One of these, and we had 2 proposals. They basically wanted. I'm going to talk about this before. We injected 2 proposals because we wanted to give the choice of people to actually vote between A and B. These 2 proposals are very similar, and they update a bit of the few variables in the protocols, let's say. In the third phase that will start in a few days, we'll spawn a test chain. A test chain is really to build confidence in this protocol and allow people to trust and to see that actually what is going to be voted on actually works. And then it is going to be followed by an activation phase. The activation, if the vote is successful, so all the bakers, all the stakeholders in Tezos are going to say yay or nay for this protocol. And if we have a supermajority of people that want this protocol to be activated, then the node is going to activate, and there's going to be one block one day where it's probably going to happen something like at 2 in the morning for us, so it's going to be really fun to celebrate this moment. The block is going to trigger this change of protocol, and the old block is going to be parsed with the protocol 003, and the new protocol is going to parse the subsequent block with the block 004. As I said, it seems easy, but actually it's not that easy, because you need also to upgrade the storage and make sure that everything checks out. I'm sorry, this is not my laptop. I'm not very familiar with this thing. Before doing this, we have 3 networks running. One is ZeroNet that is tracking the code in our GitLab in our master branch. This is done for us to test. It runs really quickly, so the time between blocks it's really short, and allows to do a lot of tests on it. Then we have and there is no real tokens on this network. Everybody can ask for tokens to participate on this network. Then there is the alpha network that it tracks what is in mainnet, but still runs with fake coins. And then there is mainnet, that is the production network. And before doing the upgrade on mainnet, we wanted to make sure. So we did the rehearsal of all the vote phase on ZeroNet. And ZeroNet runs much faster. So in 9 days, we can do what on mainnet takes about 3 months. This gives the opportunity to everybody to test the protocol, to us to actually benchmark, and to understand if there are any bottlenecks in this migration, and to build confidence in the procedure. And it's also an occasion for the community to interact and for us to interact and communicate with the community, and the community also to to understand what is this process and how to participate in it in the future. So, what if Athens? Athens is the name of the new incarnation of the protocol. We started with this kind of naming scheme following city names. So this is Athens. The next one is going to be, I don't know, be something, Barcelona. So what we did, we increased the gas limit. The gas limit is as in Ethereum, is basically the cost of running a smart contract. Since we did some pretty conservative estimations at the beginning, just based on properties, on some early benchmarks, we wanted to do a bit of more fine-grained analysis of the I/O cost of executing a contract, and this increased a bit of the gas limits in executing a protocol, and it was a feature that was asked by bakers and by the community. At the same time, we lowered the size of a role. In Tezos, to have the right to bake, so to participate to the consensus algorithm, you need to have at least one role, and one role it's right now 10,000 Tezos, and so with this amendment we lower a bit the number of Tezi that role represents. So we lower it. The proposal that won the second phase is to lower it to 8,000 Tezos. So this kind of gives people that have less Tezos to have the possibility to participate to the Tezos community, and also to the bakers and people that run delegation systems to have to redistribute in a different way the voting rights. And as well, we did a test for the invoicing. The idea of developing protocols is that the person or the company or the group of people, the community that does the development for a new protocol can charge the network for some Tezi. So this invoice for us was 100 Tezos. That is basically one beer for the 35 developers that work in Nomadic, and we wanted just to kind of make this add this code to show the community this is possible and to foster these collaborations among in the community. There is right now other people that are thinking of developing proposing the next amendment proposal for the network. So this is kind of going to be a revenue stream, for example, for developers that want to work with Tezos. And there were also other minor changes that we added in these protocol proposals, and they were mainly they were kind of more technical changes. They didn't change anything specific in the protocol. So something that I want to point out, that this change about changing from 10,000 to 8,000 is not just a variable in the protocol, because Tezos has a storage and everything, and the baking rights are computed and stored in the storage of a node. So if you change the baking right, how much is a roll, you have to recompute the baking rights. So this means that you have to do a sort of upgrade of the context, and this upgrade of the context can take times, and we had to be sure that the node wasn't going to be stuck recomputing this, and it's not going to be consume more space, etc. So it involved a lot of testing and benchmarking. Right now on really fast SSD, from when in the protocol upgrade, it can take from 10 seconds to a couple of minutes if you really run it on a hard disk of 5 years ago. That is really slow. Please don't. So the other big thing that we are working on And now I'm going to talk more about the shell part. So the protocol is, we have really the coupling. On one part we have the protocol that is the heart of how the consensus algorithm is run and how people interact in the network. The other part is the shell. The shell is basically the code that allow the protocol to run. So it implements the RPC, it's all the framework with the node, the client, the baker, endorser, and all the other moving parts. And this kind of can evolve in a different way. This is just a piece of code that we implemented in OCaml, but there is people implementing in Rust. So it's something interchangeable. And these are a few modifications that we did to our code to make it easier for people to run nodes. At the moment, the storage has become kind of a small problem because it takes about 110 gigabytes, if I look at it correctly, to run a node, and that's a lot of space. This space is because we keep everything. Everything that is passed in the network up to the moment is stored in the node. And there's a lot of information that are actually not needed to have to maintain a history of the network, like all the branches that are not been selected in a consensus algorithm, all the invalid blocks or the invalid operations, all the peers that have been connected to. These are all information that can be pruned. So for this reason, we implemented 3 types of modes for a node. One, it's the full node. The full node basically stores all the data since the beginning, but prune all the informations that are not needed anymore. It's like having an archive node where I run a garbage collector, just making sure that I keep only the linear history from the beginning to now. The second one, it's a rolling node. A rolling node, it doesn't keep the entire history, but it keeps the history up to the last checkpoint. I'm going to talk about this in a moment. This is a way to maintain a node in about 200 megabytes and having a sliding window on the history. This allows you to rebuild the history, but you cannot query, for example, the balance of something that happened 3 months ago. You can query the balance on something that happened 2 weeks ago. And the third one, it's the archive mode. The archive mode is like what we have today that keeps absolutely everything. So what I wanted to stress is that by changing the default from archive as it is today to full node, we are not compromising on the security, or we are forgetting anything. We're just removing all the, things that are not needed for the blockchain itself. And of course, a full node can still query block and operation at any point in the chain. The only restriction that we have is that if you run a rolling node, then you have you can only query informations on the sliding windows that is stored on your disk. So, a small technical point. I talk about checkpoints. Checkpoints, it's this idea that the blockchain from time to time can be considered fixed. We cannot kind of go back in history and say we fork on this side. Say if something has passed I think in Ethereum it's about five blocks, and in our system we snapshot, we put a checkpoint, automatic checkpoint every 5 cycles. 5 cycles are about 3 weeks of data. These checkpoints, it's basically to build some kind of social consensus of what the blockchain is. I can put this hash and put it on a newspaper, I don't know, write it on a wall or tattoo it on my arm. And this, if enough people do this, then there is going to be a social consensus that this is a hash on the blockchain 2 weeks ago. So up to that point, if enough people do it, I can trust whatever it's down there because everything else is linked and cryptographically linked up to that point. So what Tezos does, it stores this hash at the position 0 of a block every 5 cycles. This gives us this point in time every 5 cycles to kind of tell to the world, this is the Tezos blockchain, this is the last hash. And of course there is an RPC to ask for the checkpoints. So in a nutshell, a checkpoint basically say below this point the blockchain cannot be organized anymore by the consensus algorithm. So I wanted to give you also a few kind of technical notions. When you if you run a Tezos node, you can now you have now new command line arguments to decide the history mode. If you don't specify anything, the default is full. Otherwise, you can run a node in rolling or in archive mode. Of course, you can go from archive, a node that was in archive mode to rolling or full, a node that was full to rolling. But if you have a node in rolling mode, then you cannot switch it to an archive because you don't have these informations anymore. You can also do it in a shell file, of course. The other point that is related to this, it's about snapshots. Snapshots, it's this idea that to rebuild the history of the blockchain, you don't have to download everything from the beginning as it is now. Right now, to bootstrap a node, it takes a long time because you are going to download 110 gigabytes of data from an archive node, and you are becoming an archive node itself. We made these snapshots files. They are basically the context of a full node or the context of a rolling node. This kind of allows you to rebuild the node from a file that it's about 500, 600 megabytes, and from that moment on, you're becoming a node on the network that can query and behave like everybody else. Again, this idea of snapshots is built on the same concept, because when I download the file from somebody, this somebody also give me the hash of the hash of the last block in this snapshot. If the hash of the last node in this snapshot correspond to a checkpoint, then I can ask outside and look on a newspaper, is this hash actually on the Tezos blockchain? If this is the case, then I can trust whatever is inside in this snapshot. If it is not, then I'm basically opening myself to possible to a snapshot that is not the Tezos blockchain, basically. And again, creating a starting from a snapshot doesn't add or remove anything to the security, because you're basically rebuilding the entire history from a file instead of downloading it from an archive node. But it's important to verify this hash. So again, to bootstrap a Tezos node from a file, to create a snapshot, import. To bootstrap a node from a file that you downloaded from somewhere, you have a simple snapshot import and name of the file. This file can be full or rolling, and to this file is associated an hash file, the hash of the block. To create the snapshot itself to give it to your friends when you're sad. You can do it in this way with the export command, and this command is going to also give you the hash that it's related to this file that you have to communicate it with it. We are working on a few distribution methods, so maybe we're going to put it on EPFS and distribute it wildly like this, or we're going to build some kind of distribution methods so people can download it from website or the network. So this is my last slide, and I wanted to give a bit of the development, what is boiling in Nomadic Labs, what we're going to do in the next 6 to 10 months. So the first thing is working on this new amendment of the protocol. It's going to be the 006. And what we're calling the Emmy Amendment, as a few changes come from a paper, I think, or a conference, I don't know. This new amendment is going to be is going to be more technical. So basically, what we are changing how endorsements are included in a block. This is going to speed up the endorsement process and also reduce the number of missed endorsements that we sometimes see on the network that are caused on some delay of distributions of these endorsements. The second one that is going to be a big one, actually a huge one for us, is that we're going to change, or to propose a change, to change the consensus algorithm. Right now, the consensus algorithm, it's specific to Tezos. It's a proof of stake. It's a liquid proof of stake. And we wanted to change it to, we wanted to bring some BFT algorithm in the liquid proof of stake and adapt it. We choose the Tendermint model to do this, and we're working on basically integrating all this in our code. We're working with the CEA, that it's a research, it's a French research institution that are specialized in a distributed system and in consensus algorithm. And we've been working on it for about 3 months now, and hopefully by the end of the year we're going to have something to show to the community. This is going to be a big change in the protocol itself. Then we are going to propose updates of the shell on histories of snapshots. At the moment, the code is there, there are Docker images with this code, but we are considering still them beta, and they are not in the mainnet branch of our code. So in about 4 to 6 weeks, we are going to push them in the mainnet branch, and we are going to declare them stable. There is also more work on the shell regarding, in particular, the storage to limit the amount of space that we're using and to improve the performances. We are building also a better environment to develop dApps. This is also why partially we're here, because we are attending the ReasonML conference. We are focusing on building applications in ReasonML and also in Android, iOS, and trying to do them in kind of recycling as much code as possible. So compiling part of our code, transpiling part of our code to JavaScript, building bindings to Swift and Kotlin, and trying to compiling part of our libraries in WASM. So the idea is to reuse as much as possible what we have already done and then export it to other environments. There is also a lot of research done in Nomadic Labs about Michelson certification. So we have about 4 strong people working on an environment in Coq that it's a theorem prover. to proof certificates, and we're also going to build some kind of a library of smart contracts written in Michelson, certified in COC, that are the basic smart contracts, say multi-sig, an escrow contract, a deposit contract, RC20 contract, or something like that. And also there is a part of our group that is working on high kind of intermediate language that are going to be built on top of Michelson. They are not going to be as high level as liquidity, but they're going to have variables. What we want to provide, it's a certified compilation schema from these high level languages to Michelson, and then ask people to target their really high-level languages to this intermediate language. So this is more or less, say, the little things that we're doing in our free times at Nomadic Labs, and and I'm happy to answer any questions if there are any. Thank you.
It's on? Yeah. Okay. I have multiple questions, but I'm a really noob, so. But I don't understand this. In Tezos, you can vote, as the blockchain can vote for amendments. And what I don't understand, do the node have to be upgraded manually, or is it like? So the node itself, yes, needs some kind of, there is a person that needs to say Docker pull, Docker up -d. A node running and the blockchain changes to a vote?
No, this is the shell part.
Okay.
The protocol part, once it's voted in, if your node is running, and there are two ways basically. Either we ship the latest version of the shell with the protocol compiled in, with the latest protocol compiled in. This is basically statically linked inside. If you didn't upgrade your node is going to ask to your neighbor's node, what is the, can you please give me the code of the latest protocol that I have to run? So the code is going to be downloaded in like Tarball. The hash is going to be computed and then checked if this is the actually hash of the protocol that should be run, compiled, dynamically linked, and then this is going to run.
This is running automatically, or is it like a?
Automatically, yeah.
Okay. Then another question is like you mentioned like since the bytecode or the quasi bytecode, the intermediate representation is easy to read, there's more confidence in the smart contract. So what I don't understand, where's the difference to say liquidity, solidity in Ethereum, where I can check the hash of the bytecode, of the compiled bytecode.
Can you read the bytecode? This is the point.
Yeah, but I still can read the source that is used to compile the bytecode. And I can check the hash of the compiled bytecode?
Right. I mean, I buy your thing. What we have a certified interpreter for the Michelson code. So the interpreter itself comes from a proof. It's a mathematically proved object. The code, the Michelson code itself, has a proof that check some properties of it. And from the intermediate level code, there is a certified compilation step. So what we are trying to provide is really from the high level code to the bottom part of it, a certified path where things should not go wrong. So
basically there are less bugs, like possible, like
it's not about bugs. It's I mean, if you write a bad algorithm and you prove that this algorithm is bad, then it's going to write. But it's about providing the possibility of making sure that your algorithm does exactly what the specification says.
Yeah, then is there another one? Like, I have multiple questions, but I don't want to take the time for.
Hi, Andrew from Happy Tezos. I just wanted to say thank you for introducing the snapshot modes and archive mode.
Yeah.
So we're running it on like third of our nodes for 3 weeks now without any issues. So I would like to encourage everyone to just try it out and use it.
This is a really good news. Thank you.
Thanks.
From security point of view, can you compare Michelson or actually smart contracts in Tezos to Ether or Ethereum? Was the killer feature, or why they are better?
From a security point of view.
Yeah, because in Ethereum there is like a really huge issue with security. Actually, if you are like smart code developer, you cannot sleep in the night, right? Because you, yeah, it's true, and I think from my experience, the biggest reason to switch to the Tezos is the security and actually a lot of different assurances. And I would love to hear your point of view on.
I mean, for me, writing a contract has two things. One, you write the code, and the second thing, you write the specification of what your code should do, and then you match the thing. So you actually prove that your code does exactly what you want. If you didn't get it wrong, these two parts, then we are providing the tools to make this path secure as possible. And we are using well-known techniques that comes from academia, but they're also used in industry to give the developer as many insurances they can, and give back the slip to the developers. It's the idea that you cannot get wrong like a variable assignment because there is some I don't know, some hidden part of your code that you didn't explore. If it's mathematically proof, it means that I have done an exhaust search of the execution spaces, and it cannot go wrong.
Basically, formal verification.
Formal verification. This is this is our main security features. Formal verification.
Hi. I was wondering when you said that when you upgrade the protocol, it's not just upgrading of the code of the protocol, but you need to sort of reindex or do some changes in the storage.
Yep. Okay.
And I can understand why it is, but and I was wondering now when you introduce the snapshots, how does it apply to the new model of snapshots? Does it mean that for example, it runs really fast when you are on the snapshot and much less data, or is it independent whether you run with snapshots or without, regardless of the mode of the node, or what's how one should how these two interact, or do they interact at all?
Mm-hmm. So basically, if you do an upgrade of the protocol on an archive node, and we are keeping track of all the balances from the beginning of time, you have to recompute all these balances and all the writes from the beginning of time. And this can take a lot of time on 120 gigabytes of stuff. If you keep only a full node, you don't keep everything. You only keep a part of it. So of course it's going to be faster because it's going to compute this, doing this part of the code that we call stitching. Stitching is basically from the last block of the old protocol to the new block, to the first block of the new protocol.
And I presume the answer is yes, but still, is it not that when you are doing this upgrade of protocol, you might need some data which you don't have in the snapshot? Where you somehow rely on the history, how that evolved to the snapshot, or it doesn't?
I mean, we have all the data on the chain. So
yeah, sure, you have. But when you do an upgrade on a node which is not running this archive mode, but is running on a rolling node, cannot it happen that it's for during the upgrade it is missing some of the data which which it lost sort of in the snapshot?
I mean, the data that we are changing is basically the context of the node. In this context, we keep track of the balances, the delegates' rights, the latest operations. We can, in theory, with the full node, recompute all this information down to the beginning. Yeah. We don't keep it because it takes a lot of space, but we have all the information to recompute them. And of course, we are not, I mean, at the moment we haven't implemented, but we might implement also this reconstruction. So at a certain point in time, you want to know what was the balance 3 years ago. So this idea of minimizing the change, minimizing the upgrade on the smallest subset of data is not going to compromise anything about what is there. It's just going to consider less information. Thank you.